Hello again. This is another video. This time it is a gas power cycle with regeneration. This is 9.57 in the 6th edition. Wait here if you want to see all the knowns for the problem, but we're going to move on to try and keep the video short. So, to begin, we are trying to find something, or all the values associated with state 1. You know, your H's and your PRs. So, we are given temperature of state 1, and since this is air standard analysis, we can just go to the air tables, which is A22E, and just look across the table and find all of our values that we need. So we found that H1 is to be 124.27. And PR1 to be 1.2147. And now, using the relative pressure, we're going to, or PR value, I guess, we're moving on to try and find something about state 2. And so, this will be a value for state 2S, because remember, using relative pressures, it is those are S values. Those are with S. These are perfect isentropic relationships. So this is state 2S. And so we have PR2. Let's see if I get this one right. Over PR1. Yes, I did. Is equal to the compression ratio, or the compression ratio, which is CR. That's how I write it. And so we have PR2 is equal to CR times PR1, which is, let's see what we get here. I can't remember. I think it's like 9 or something. See if I'm right. I don't know. Can't remember. Maybe I can't remember either doing the problem. Oh, 17. Yeah, 9, 17. Same thing. So our PR2 is 17.0059. 58, apparently. Either one. And so, then from that PR value, we're using the tables to fix the state. So we're finding H2S and I guess T2S if you need it. But I don't think you do. So I think I found it either way, just because I like to find all the values. So, and this little part will get you H2S to equal to 264.116. And a T2S value of 1092.51. And moving on. So now that we have the perfect case, the isentropic case, we have to use our, since this is going through a compressor, we're using a equation through the compressor. So next up is to find the values at state 2, not 2S, 2. So we're fixing state 2 using the values we found for 1 and 2S. So this is using the compressor equation, which we've been using for a long time now, but if you don't know what that is, I'm sure I'll write it in a second after I erase that long tail on the parenthesis. Yep. Parentheses. Anyway, what's a singular parenthesis? So using the efficiency equation. And the efficiency equation, I think, for a compressor is H2. Well, for this case, it'd be H2S minus H1 divided by H2 minus H1. And what we're doing is trying to find H2. So we're going to, just like we've done in previous cycles, you know, we're trying to solve for something at the second state. the non-ideal case. So solving for H2. Which I circle it, I think, yes. And so from there, we just manipulate the equation, and you get this right here. I think it's H2 is equal to H1 minus, I think that's what it is, H1 minus, or no, H1 plus H2S minus H1 divided by the efficiency. Yeah. Always have to think about it, because they switch, they switch addition and subtraction from compressor and turbines, and the location of the efficiency changes from divided to, or multiplied to divided. So, always got to think a second. Thinking's hard for me. And so, we find from this equation H2 to be equal to 292.76 and so since we know H2, oh wait a minute, I think this is where I did something wrong. Yeah, I'm trying. No, wait a minute. H2 to to fixed state. So I have to find all the other values associated with state 2. I think. Yeah. And that means just the temperature, I think, is all we need to find here. And so, H2 we find to be 292.76, and T2 to be 1206 Rankine. And so, oh yeah, I wrote pressure, but there is no PR associated with this. We already used that for the isentropic case, so this was a little bit of a brain fart for me. But anyway, then back to circles. No squares this time. And then moving on. So now the next part is we can't solve for state X yet. If you follow along in the diagram at the beginning, you can't solve for state X yet because we don't know anything about the regenerator at this point. So we're going to skip it and move into state 3, which is after the combustor. So after all the heat was added. And so we know the temperature at state 3. It was given in the question. And so, since it was given in the question, we can just go right to the table and solve for all the state 3 values. In A22E. And so, what we find here is that, well, this is what was given. So T3 is equal to 2500 Rankine. And that means that H3 is then equal to 645.78. And then PR3 from the same line is 435.7. Alright, so now that we have those values, that solves where state 3 is going into the turbine. And so, now we have to find something else. We have to start solving for state 4. So what we have to do is find the perfect case. We have to fix state for S. So the ideal case, perfect case. And this is across the turbine, as I said before. And so, we are going to use a similar relationship that we did earlier. This is pressure rate, or it's the pressure going across the turbines. or going across the turbine, which is PR3 over PR4 is equal to, it's CR. And so, I know what most people might say is PR4 over PR3 is 1 over CR. I think it basically, as long as you know the relationship, it doesn't matter. You just know that the pressure has to drop as it goes through the turbine. So you know that PR4 has to be smaller than PR3. So therefore, you just know to divide PR3 by the compression ratio. Like I said a similar thing in the diesel cycle video. It's just the way that I look at it. I don't try to remember the equation because I know I'll always mess it up. So I just remember what things need to get smaller in order for it to make sense. Because turbines, they expanded, which means you know the pressure is going to drop. So if you get PR4 to be higher than PR3, that doesn't make any sense. That means it didn't get expanded. It means it got compressed. And so your turbine sucks. Or your turbine is not a turbine, it's a compressor. And so from PR4, you can find H4S to be 313.36. And so, now that we have state 4S, we are now going to do the similar thing that we did when we did the compressor. So we have to find state 2 now, or not like we did with state 2, we have to find state 4, the normal state 4, the actual state 4. So we're doing the same thing, use the efficiency of a turbine instead of a compressor. And with this, we are fixing, to fix the state, I forgot I was writing more things. Look at me droning on. So, the efficiency of a turbine being H3 minus H4 in this situation, divided by H3 minus H4S. And so we are solving for H4. As you can see, from my circle. And so, H4 is then equal to H3 minus it's the eta, so it's eta turbine, which I think in this case is 87.87 times H3 minus H4S. And from that, you get H4 to be equal to, where did I put that? Oh, well, I found it. 356.574. And then you get T4. Well, I think you do. I don't know if I found it, but I know you can find it. How about that? Okay, I did not find T4. And so, now we find all values associated with state 4, which this is where I put down the temperature, I think. Which is 356, so this is just our H value again, 0.574, and this is temperature 4. Huh. Don't know where I put that. Oh, there it is. 1452 degrees Franken. Okay, and so now that we have that's H4, so we have 1, 2, 3, and 4. We need X and so basically we need to solve for the regenerator. This is the next part. And so, in this situation, we use the regenerator to solve for the state X, which is right before the combustor. So basically state X is the product of the heat added between the regenerator top part. You know how the top is the exhaust and it's giving heat to the bottom part of the cycle? It is the product of that. So it's basically state 2 plus the heat added. I guess the difference between 4 and 2. So this is the regenerator efficiency equation, which is Hx minus H2 divided by H4 minus H2. And what that means is basically that's the heat gained between X and 2, divided by, I guess, the difference in the two differences, the big differences. You have the hottest and you have the coldest part of it. And so Hx, if you manipulate that equation, you get H2 plus the efficiency times H4 minus H2. Which means Hx is then equal to 350.193. So, moving on to the next part. Now that we have Hx, we can then just go ahead and start solving the actual question. So this is just saying what the solution is. Getting up, stretching my legs. Getting some water. It's hard to talk. I'm doing this live from my bedroom, so back home in lovely Decatur, Illinois, on spring break. This is how I spend my spring break, making videos. So this is the solution to the problem. The first part is the work net of the cycle. At least I think so. No, wait a minute. This is where I messed up. It's not the work net of the cycle. The first part is we're trying to find the volumetric flow rate going into the compressor. But I gave you a sneak preview because I thought we were asking for the work net, but it wasn't. I realized it in a second, so bear with me here. I start to realize that the work net was just a means to an end. So I'm going to get rid of that in a second. Yep. So what we were actually trying to find here is the volumetric flow rate, like I said. This part's kind of tricky. So if you get this on an exam, you really have to kind of think about what you're doing here, because you're getting numbers from two different sources on the cycle, and they have to kind of work together to find the volumetric flow rate. And so it's going into the compressor. That's what I said. So volumetric flow rate going into the compressor. And so what we have to do here is we need to get two things. We have to have the mass flow rate, and we need to know the specific volume, because if you remember from that equation, it's the volumetric flow rate equation that relates to mass flow rate and specific volume. I think it's AV, so area times velocity, divided by specific volume is equal to mass flow rate. I think I write it out here, but yeah, see, if you moved over the specific volume, you'd get the equation I just said, because area times velocity is volumetric flow rate, I guess you could say. And this is where you get it from. See, I did write it. What a nice guy. So we need to find, as I said, specific volume and mass flow rate to be able to solve for AV being volumetric flow rate. So I think the first part, I think we solved for mass flow rate. Quite possibly, I can't quite remember what I did first. Maybe specific volume. We're finding specific volume first. Staying on my toes. So, and we are doing this using the ideal gas law at the beginning of the cycle. Because at the beginning of the cycle, they gave us a lot of information that we haven't really used. Well, we haven't used it. Like, for instance, they gave us the pressure, they gave us temperature, and so we didn't use the temperature yet. And so we now are using the temperature. We didn't use the pressure yet. We're now using the temperature and pressure. And so we're solving here for specific volume, which is volume over mass, big V over mass. And if you manipulate that, you end up getting RT over P is equal to specific volume. And so this is where units come into play. Whenever using the ideal gas law, it's kind of confusing, especially in English units. So hopefully I write out something, these units. That right there is just R. That's big R, not R bar. R bar is the first part, the 1545. And so then we divide by pressure, which is 14 pound force per inch squared. But there's some conversions here that need to be done. This one you have to multiply by 144 to get it into feet. And then that feet flips around and you end up getting, because we're trying to get this in feet cubed per pound. There's a pound on the top, there's a Rankine on the top, they cancel. The pound stays on the bottom. There's a foot on the top too. When multiplied by the 2 feet on the bottom, get you to feet cubed, and then everything else cancels. The pound force cancels, and you end up getting feet cubed per pound. It's kind of hard to tell that whenever I didn't write out the units for the R, but that's what's happening. And I think I'm taking a second here to make sure I have the units right. Oh no, wait a minute. This is because I didn't have this number written out. I didn't have V written out. And so I had to do it really fast on my phone. So 13.75 feet cubed per pound is what you get when you do that calculation. I hope. So then we move on to finding the mass flow rate. The mass flow rate is using the work net equation. We were given work net in this question. It's 5 times 10 to the 6 BTUs per hour. And so, using that knowledge, we can write out the work net equation, which is, I think it's work turbine minus work compressor for this problem. And so if we write out that in terms of enthalpies, this is what you get. Well, maybe. We'll see if I can get to it. Yeah, 5 times 10 to the 6th BTUs per hour is equal to H3 minus H4. Man. Really thinking. I can hear the gears creaking. H2 minus H1. So minus H2 minus H1. And this is multiplied by the mass flow rate. And that is what we're trying to solve for. So obviously we just divide over that whole quantity. And we get mass flow rate to be equal to. No, we've got to insert a new page. We get that to be equal to that division, I guess. So 5 times 10 to the 6 BTUs per hour divided by that quantity. I'm not sure if I write it out or not. I think I do. Yeah, I do. So that's H3. That's H2, or H4, sorry, minus H2 minus H1. And so, once I finally get around to writing this, we'll end up getting a number, and that number is the mass flow rate. But remember, this is different units. The problem asks for it in BTUs per minute. And so I have to change the top parts in BTUs per hour. And once again, I did not have this calculation handy. I only had it in BTUs per minute. So I'm going to have to, I think I write this out. I had to do it on my calculator again pretty fast. Divided by 60. So it's 1 hour, 60 minutes an hour. You get the drill. And then we end up getting 690.3369. And that is in BTUs, or pounds per minute. And so, our volumetric flow rate is just equal to the multiplication of mass flow rate times specific volume, which gets us to be 9496.28 feet cubed per minute. And that is the answer to part A. Part B is just asking for the temperature after compression. But I thought it was the max temperature of the cycle because usually that's what it asks for. I'll figure it out in just a second. Give me some time. Hear the old mouse running on the spinning wheel. And I figured it out. You can almost see the moment in which the light bulb turned on. Like right when the mouse starts moving. It's like, oh man, I messed up. So, now I'm going to erase that. And move backward a little bit. And so we are looking for the temperature at the end of, at the end of compression. So basically, temperature 2. And if you remember, we have found temperature 2 already. I made sure to highlight that, even though you didn't have to solve for it, you did. You did, but at that moment you didn't have to, so I didn't have to come back to it, you see. I was thinking ahead. I smart. So T2 to be 1206 degrees Rankine, which is what we found earlier. And so the final part, part C, is the thermal efficiency of the cycle. So the thermal efficiency of the cycle is just work net over Qn. And so work net over Qn, very simple, it's just what we found earlier. Or you could do, I mean, there's different ways to do it. I think I wrote this one, just to talk about it. 1 minus Q out over Qn, which is equal to 1 minus, I think it's H4 minus HY or something like that is Q out. Or no, I can't remember the equation, but basically there's two ways to do this part. You can do it that way or this way. This way is the way I did it, which is work net over Qn. And I think I even checked this to make sure this is the same answer, and it was. I did it using their answer and mine, and I got the same thing. So if I'm wrong, just let me know. But this is just your simple thermal efficiency equation, and you work with it from there. And you get a thermal efficiency of 40.1% whenever you insert all the H values in there. And that's the last part of this question. I hope everything made sense. I think I'm going to do a doodle really fast. Yes, I am. Classic. But yeah, that equation for the other way of doing thermal efficiency, you can look that one up. It has to do with the Y, the exhaust gas leaving the cycle, but I did not do it that way because that solves for another variable. But we did it. All right, well, thank you for watching, guys.